Okay, here we are with section 2.3. This is our last section for this chapter, and let's go. Our objectives are convert quantities from one unit to another using appropriate conversion factors, identify the independent and dependent variables in an experiment, evaluate and make inferences from data represented graphically, and communicate valid conclusions supported by the data, express and manipulate relationships among physical variables quantitatively using graphs. Our assessment questions, which we will come back to at the very end. Which of the following unit conversions is correct? Look over these conversions and figure out which one is correct. A marble was dropped from varying initial heights and its final speed measured. Identify the independent and dependent variables in this experiment. As the marble fars farther, its speed decreases, increasing, or remains constant. All right, the equation is going to be speed. It's also for velocity, but speed is the distance divided by the time. All right, converting units. When solving physics problems, you may need to convert units to make them consistent. On page 58, I'd like you to click on the converter and take a look at that. It's on page 58. How many meters are in 1 mile? How many kilograms are in 1 solar mass? How many hours have you lived by your 18th birthday? Basically, you can use the converter and put these in there, and it will tell you the answer. And this will give you a heads up on how to do this. We're going to be doing some dimensional analysis this year, and this is one way to do it. So you should have got 1,609 meters, 1.99 times 10 to the 30th kilograms, and 158,000 hours. When solving physics problems, the units you use must be consistent. You need to be able to convert units to make them consistent. 1 kilometer is the same as 1,000 meters. 1,000 meters, the same as 1 kilometer. To convert a quantity from one unit to another, multiply by a conversion factor. A conversion factor always has the value of 1, whether it's right side up or upside down. That's just using the metric system. It's not always that way if you don't use the metric system, but if you're going through the metric system, yes, your conversion factor will be 1 and then some power of 10. Here are some examples of conversion factors for length. They have ones for inch, meter, feet, miles, and different things like that. To convert from one unit to another, multiply by the appropriate conversion factor. Pick the conversion factor that lets you cancel the unit you don't want and end up with the unit you want. So if we had, here, let me do this, 3,200 meters, I'm wanting to cancel meters and get to miles. So what happens is these cancel, leaving me in mile, because 1 mile is 1,609 meters. So I have 3,200 divided by 1,609 equals 2 miles. Use the conversion factor shown at the right to convert 12 inches to centimeters. So take a look at this. If you want to go, you are going to start with, I'm sure it's going to pop up after I do this, 12 inches. So we want to convert 12 inches to centimeters. And we know that 1 inch is equal to 2.54 centimeters. So if I'm going to convert that, let's take a look at what happens. See what happens here? They flipped what they gave up here. This is 1 inch is on top and 2.54 is on the bottom, but we want to cancel the inch, so we flipped it to where 2.54 is on the top, because this will cancel with that. So 12 times 2.54 will then give me 30.5 centimeters. Flipping the conversion factor upside down lets you cancel the unit you don't want and end up with the unit you do want. All right. Data can be displayed in tables, graphs, and charts. In this lesson, you will use all 3 methods. So we have a table, a graph, and kind of a pie chart. A chart can also be thought of as a graph. Data and tables, this work with a partner to answer these questions, or since you're going to be home taking these notes. How is temperature changing over time? So what is happening to the temperature as time passes? Predict the temperature at 50 seconds. So what would the temperature be? You need to figure out what's happening here. How is temperature changing over time in this one? predict what it would be at 50 seconds. So now, what's happening to the temperature as time passes? That's right, it is decreasing. It will be roughly about 10 degrees Celsius. An experiment may choose to manipulate one variable, the independent variable, to determine how this will affect another variable, the dependent variable. These are important to know which one's independent and dependent. This experiment, experimenter chose to record speed over a certain time interval. So we have speed on this axis and time on the x-axis. The independent variable is time and is plotted on the x-axis. So x equals independent. That means y equals dependent. The dependent axis. Test your knowledge. Louise measures the air temperature at noon every day for an entire year. She wants to graph her findings. Which is the independent variable and which is the dependent variable? So she's got a graph over here. So the independent variable was the day of the year and the dependent variable was the air temperature. So which of these graphs show a greater change in energy? Well, if you look at this, this is going from what, 150 up to about 175, and this one's going from 150 to about 175. So which one shows the bigger change in energy? Question, which one? They both show the same amount of energy because they both are measuring the same thing. It's just this one is easier to read than this one. Visualizing data. Plotting data can reveal mathematical relationships between variables. Equations can be found to fit the graphs and model the relationships. Scatter plot. The plots are just going everywhere. This is kind of random. A linear equation. This is where you get the y equals mx plus b. Inverse. Y equals 1 over x. And nonlinear. Y equals ax squared plus b. In Investigation 2B, you will find the equations needed to fit a set of graphs. Click the interactive simulation on page 61. So you're going to click this on page 61 and work through this. I want you to work through as much as you can and see if you can figure a lot of these out because they're pretty straightforward. All right, the simulation contains data showing how some variables change under different conditions. The 4 examples include an object with constant speed, an object dropped from rest, carrying current varying with resistance, and object cooling over time. So it gives you instructions on how each one of these works, how to choose choose quantity for x and choose quantity for y, table mode, model mode, enter parameters, quantity of mode, and choose equation which to model. This is the big one that I want you to see. And if you just want to do the first two here, object with constant speed and object dropped from rest, those two are fine. We'll get to these other two later on. So object with constant speed and object dropped from rest are the ones I want you to really focus on. Matching models to data. Plot time on the x-axis by selecting x for column 1. Plot distance on the y-axis for an object moving at constant speed for y for column 2. So this is going to be the constant speed one right here. Choose a model equation, line, parabola, exponential, inverse to try to fit the data. So you're going to have to choose from one of the ones that we had, the 4 choices. Change parameters for that model to try and fit the data. So you're trying to fit and make it match. Okay, what model and parameters are a good fit to this distance versus time? So you have distance and time, and you have a line that goes up just like this. What model was that? Are equal numbers of data points plotted above and below your model? Why is this important? Repeat these steps for an object dropped from rest, 1 and 3. So you just have to do the 2 of these, the object dropped from rest, which is here, and then the first one. Don't worry about the last 2. All right, don't worry about doing these. So we're Xing out the current resistance and we're taking out of the temperature and time. Investigation. Other ways to represent data, pie and bar charts. Use the data below to construct a pie chart, bar chart, and stacked bar chart. Be sure to label your charts. Maybe if you read these, you're going to read at the bottom. It gives you all of these different parts, and we have a pie chart. We have a bar chart. Okay. If you have trouble with the bar charts and the pie charts and stuff, let me know, and we'll go over it some if you want to come in and talk to me about it on Tuesday or Wednesday. The equation for speed is, it kind of dropped down that speed is distance over time. If you hold the distance constant and graph speed versus time, what kind of relationship will you get? Linear, parabolic, or inverse? So we're looking for what would it look like if you hold the distance constant, so you have velocity and time, or no, distance and time, sorry. What would it be? It would be inverse. You see how the graph goes like this? It goes down and around because your distance would end up doing that 1 over the time. Because you're keeping the distance being 1, and as time increases, the graph looks like this. Visualizing data. Plotting data can reveal mathematical relationships between variables. Scatter plot, there's no relationship. Linear, this is one you probably have seen before to find the slope of a line. Here's one, y equals 1 over x, and here is y equals ax squared plus b for the nonlinear. These are the most common that we end up seeing, with this being the most common. All right, which of the following units conversions is correct? So we're back to this. Which one is correct? Which one has its units cancel? B, it is this final answer, round to the correct number of significant figures. Marble was dropped from varying initial heights and its final speed measured. Identify the independent and dependent variable. So dependent variable is the speed, independent variable is the height. And as the marble falls farther, its speed will decrease, increase, and remain constant. It increases because when you drop something, gravity makes it go faster and faster, and we'll talk more about gravity next. See you in the next chapter.